Thank you for inviting me. Sorry, this time I couldn't participate locally online. So today I would like to talk about the recent progress in coherent diffraction imaging at SPring-8. So regarding the outline of my talk today, I'll talk about high-resolution coherent X-ray diffraction imaging with focusing mirror optics at SPring-8. Then I will talk about two ptychography methods. First one is a spectroscopic ptychography. The second one is a multi-beam X-ray ptychography. Then I will show you our recent work that is a single-frame coherent X-ray diffraction imaging of extended object. So finally, I will give you future perspective regarding the new synchrotron radiation facility in Japan. Okay, let's start with high-resolution coherent X-ray diffraction imaging with focusing mirror optics. So the motivation here is to observe small structures by X-rays. So as you know very well, coherent X-ray diffraction imaging is a lensless X-ray microscopy technique which utilizes coherent diffraction pattern measurement and phase retrieval calculation, which is beyond the spatial resolution limitation of X-ray microscopy. The principle is very simple. This is the schematic of plane wave CXDI, the classical CXDI and the transmission geometry. In this geometry, isolated sample is illuminated by full coherent X-ray beam with a plane wave field. The coherent diffraction pattern from the sample is observed in a far field, which is measured by a two-dimensional detector. So diffraction intensity don't include phase information on scattering X-rays, but when we measure diffraction pattern over sampling condition, then by applying phase retrieval calculation to the diffraction pattern, phase of scattering X-ray is iteratively recovered, and simultaneously sample image is reconstructing computer. So coherent X-ray diffraction imaging can quantitatively evaluate electron density distribution and strain of thick object at high spatial resolution. This is a significant advantage compared with well-established electron microscopy technique. So in the early work, we observed precipitate buried within aluminum alloy and human chromosome, but the resolution was not so good. So the improvement of spatial resolution was one of the important issues. So what should we do to improve the spatial resolution of CXDI? So the observable coherent X-ray diffraction pattern can be understood drawing the about sphere. This is a part of about the surface. So diffraction limited to resolution length is expressed by this equation where lambda is wavelength, theta max is angular acceptance. So this means that the high Q diffraction data are necessary to improve the spatial resolution of CXDI. However, the diffraction intensity rapidly decay at high Q region. Therefore, we need high intensity X-ray to collect high Q diffraction pattern with good signal to noise ratio. So in order to improve the spatial resolution of CXDI, X-ray focusing is the most effective approach. So we selected mirror optics here that is excellent regarding the focusing efficiency and radiation hardness. So we've been developing high resolution diffraction imaging apparatus installed with mirror optics at SPring-8. So SPring-8 is the third generation synchrotron radiation facility in Japan where one can use high brilliant X-ray beam. And fortunately, I could easily get a suitable mirror for high resolution CXDI. That is an Osaka mirror, which was originally developed by Professor Yamauchi's group of Osaka University. So now one can purchase Osaka mirror from JTEC Corporation in Japan. This mirror has a high accuracy surface shape and realize high efficiency X-ray focusing and speckle-free illumination. So we have developed high-resolution CXDI apparatus with Osaka mirror as KB optics, which can focus two-dimensional X-rays. So X-ray beams were focused about 1 micrometer spot size on the sample position. So the flux is about 10 to the 10th photons ordered at 12 keV. In the first demonstration experiment, on the sample, we used a 100 nanometer size silver nanocube sample. The important thing is that when the sample size is much smaller than focus spot size, one can regard that the plane wave illumination. So this is the measured coherent diffraction pattern of the silver nanocube. You can see the very clear cross-spectral pattern, which is due to the cubic shape of this nanoparticle. So you can see the similar pattern in the general textbook of optics. That is Fraunhofer diffraction of the square aperture. So we estimated structural resolution resolved by X-ray diffraction. So 3 nanometers here, the 2 nanometers here. The highest Q spectral pattern was observed at 1 nanometer half period resolution, although it was a little bit noisy. So this is a reconstructed image from this pattern. You can see the very clear square image of this silver nanocube corresponding to the projection of electron density distribution of the nanocube. The pixel size of this is 1 nanometer. The edge resolution is 2 nanometer. So I think which is still world record of the resolution of X-ray microscopy now. So we also applied this high resolution CXDI to the 3D electron density mapping of gold-silver nanobox particle. So it is known that the gold nanocage particle with hollow interiors produced by using galvanic replacement reaction from the silver nanocube. So nanocage particle is a promising material for some medical applications, understanding the mechanism of the shape control processing important to design and fabricate new nanoparticles. Here sample, we choose a gold-silver nanobox particle that is intermediate in this processing. So we measure 62D diffraction pattern of the isolated gold-silver nanobox particle at 60 instant X-ray angle and then reconstructed through the image. So this is a surface rendering of the nanoparticles. The voxel size is 4.2 nanometer. It's a very high resolution where threshold electron density is set to this value. And you can see that there are small pieces on the surface. Next, when we set the threshold to electron density of pure FCC silver, the hollow interior appears. So these are the cross-section images of 3D images. The resolution is better than 10 nanometer. So that's a high resolution. So here we should note that this imaging technique has a one limitation, that is the sample is limited to isolated object less than 200 nanometer. So X-ray ptychography, that is the scanning type of CXDI, that is a breakthrough overcoming the limitation, which can observe extended object. So which was first demonstrated by John Rodenberg group in 2007. And X-ray ptychography, the object of interest is scanned in small step by overlapping probes, providing redundancy and collected data. The sample and probe are reconstructed by using phase retrieval calculation, that is extended ptychographic item range IPAM. So in order to obtain high resolution images in X-ray ptychography, in addition to the increasing the instant X-ray intensity, beam stability is also very important. We developed temperature stabilization system. Temperature change of the apparatus in 12 hours was suppressed to less than 0.02 degrees C. And we also developed drift monitoring and a collection method using a reference hole on the sample. Here's the time dependence of the beam drift at the sample position. Accumulated beam drift for 10 hours in 150 nanometer horizontally and 450 nanometer vertically. So which was sufficient for ptychography measurements, short-term measurement. However, long-term stability was still insufficient and the probe changed after a few days. So in order to further improve the stability, we developed advanced KB mirror optics for ptychography measurement. So conventional KB mirrors consist of pair of elliptical surface shape, and focal position is very sensitive to the glancing angle due to coma aberration. On the other hand, advanced KB mirror optics can compensate for coma aberration by combining elliptical and hyperbolic surface shape. So Professor Matsuyama of Nagoya University has developed monolithic advanced KB mirror optics, which has an elliptical and hyperbolic surface shape formed on a single substrate, so which can focus with the same procedure as a conventional KB mirror optics. So here is the appearance of our recent ptychography apparatus with advanced KB mirror optics at SPring-8. This mirror unit chamber is purged with helium gas and located inside the heat insulator panel, and the mirror is installed here. The sample was placed in a vacuum chamber, and the flux on the sample position was 2 times 10 to the 8 photons per second at 6.5 kb. The diffraction pattern collected by Dector's Eigen 1M detector installed in the vacuum chamber here. So this is the result of the drift evaluation. The accumulated drift for 7 hours is less than 100 nanometer for horizontally and vertical directions. So the drift is greatly reduced compared with the conventional KB mirror optics. So next, I show the reconstruction result. In the performance test using a test chart, so we clearly reconstruct a minimum structure of 50 nanometer by the PLTF analysis. The full period spatial resolution was estimated to be 12.1 nanometer. So regarding probe stability, the probe function almost doesn't change after 3 days. So we established high resolution and high stability ptychography measurement system using advanced KB mirror optics. So so far we have applied high resolution X-ray ptychography to structural imaging various samples, for example, nanoparticles and biological specimen, and integrated circuit. So the origin of the image contrast is phase shift of instant X-ray wave field that is corresponding to the projection electron density distribution of the sample. So now 10 to the 50 nanometer full period spatial resolution is routinely obtained. So next is the X-ray spectroscopic ptychography. The motivation here is to visualize chemical state of bulk materials. So X-ray spectroscopic ptychography combines X-ray ptychography imaging with X-ray absorption fine structure, that is the ZAFS spectroscopy, which provides structural chemical imaging at nanoscale. But X-ray spectroscopic ptychography is not easy. This is because the amplitude contrast, which is reflect absorption of instant X-ray, is very small compared to the phase contrast, especially in the hard X-ray region. So absorption is very small, so making it difficult to reconstruct amplitude images. So in order to improve the convergence of phase retrieval, so here we propose the use of Kramers-Kronig relation in the phase retrieval calculation. So in X-ray ptychography, complex transmission function is reconstructed as a sample image, which is expressed as this equation. The red part is amplitude term, and the blue part is a phase term. The beta and the delta, are described using the normal dispersion term of scattering factor as shown here. So F1 spectrum is related to the F2 spectrum. This is known as a Kramers-Kronig relation. So when we apply this equation to the Kramers-Kronig relation, we can derive this equation. This equation can be used as additional constraints in phase retrieval algorithm for reconstructing complex valued image from the multiple energy ptychograph diffraction data set. I called it KKR constraint. So next, I will present some of the application by X-ray spectroscopic ptychography. The first one is the ceria zirconia catalyst particles that is called CZ. So this material has a stoichiometric oxygen region release in a crystal bulk with a high efficiency at 90%, and it is used as a co-catalyst of automobile exhaust purification three-way catalyst. So during the oxygen region release, the framework of the crystal structure is maintained with the oxygen atom getting into out from vacant side, and the cerium balance change between 3+ and 4+. So our concern is to visualize the cerium balance related with the oxidation state in a CZX particle at nanoscale. So we prepared 3 kinds of the PTCZX particle, CG7 and 8 and 7.6. CG7 is the oxygen release state. CG8 is the oxygen storage state. CG7.6 the intermediate state of storage. That is the most important sample of this experiment. So we measure ptychography diffraction pattern at 33 energies, cerium L3 absorption H, and simultaneously monitor the instant X-ray intensity by using ion chamber. It takes 6 hours for each sample. This is SEM image for CG7 and 8 and 7.6, and amplitudinal phase images by ptychography at 5.732 kb above the absorption edge. And the pixel size of reconstructed image is 13 nanometer. Spatial resolution was evaluated to be 40 to the 50 nanometer by PLTF analysis. As you can see, X-ray ptychography image agree well with the SEM images. So next, we visualize Selenium valence of the PTCG particles. As a procedure, so first we derive the Zane spectra of CG7 and CG8 from the amplitude images. So then spectra PTCX can be approximately expressed by a linear combination of the normalized Zane spectra of PTC7 and 8. So parameter A and B, each pixel was determined by the least square fit analysis, and then derive the Selenium valence map of PTC7 and 8 and 7.6. White and red color present Selenium 3 plus rich state, and blue and green color present Selenium 4 plus rich state. So we found that the CG7 and 8 show the almost uniform Selenium valence, and the CG7.6 show the heterogeneous Selenium valence distribution. We want to know here the internal valence distribution. So then we tried 3D valence imaging by 3D X-ray spectroscopic ptychography. As you can easily imagine, that is a very, very challenging experimental reconstruction. The experimental condition here, the sample is only one sample, that is a partially oxidized PTC 7.6. So we measure ptychographic diffraction pattern at 28 energies from minus 75 to 75 degree in a 2.5 degree step. The measurement time was 5 days. The number of the major diffraction pattern is more than 100,000. So this is the result of 3D visualization of Selenium valence of the CGX particle. Voxel size of the image is 14 nanometer, and number of the voxel is 27 millions. As you can see, the outermost surface is completely blue, which means completely oxidized on the surface. The internal valence distribution is quite complicated. So this is the first 3D visualization of bulk materials in the 3D at the nanoscale. Okay. Next application is a battery material, that is LNMO, so which is known as a promising cathode material for a next generation lithium-ion battery because of its high energy density and high working voltage. But there are some problems for practical use. One is the rapidly capacity fade during charge-discharging cycling. There are two types of LNMO, ordered and disordered structures, so which have advantage and disadvantage. So distribution of order and disorder LNMO in the particle level is unclear. So our concern is to visualize the microstructure, chemical state, and LNMO particle. So the sample was as synthesized LNMO particles, and we measure ptychographic diffraction pattern at the manganese and the nickel K-absorption edge, and total measurement time was 18 hours. Here is the SEM image of the sample. By analyzing the ptychographic phase and the absorption images, we derive the chemical state image, as shown here, reflecting the manganese mole ratio and electron density and the manganese valence. We found that the chemical state is heterogeneous. Then we classify the three correlation group by data clustering approach. So we visualize the ordered and disordered phase and the minor phase of these particles. Okay. Okay, next, another ptychography method, that is multi-beam X-ray ptychography. The motivation here is for highly efficient use of synchrotron radiation. So synchrotron radiation provides partially coherent X-rays, and the coherence ratio is very small, less than 1%, at 6.5 kb in the SPring-8. Even the SPring-8, that is a planned upgrade project of SPring-8, that is about 10%. So to ensure spatial coherence of the instant X-rays for quadrant slit is set upstream of the sample. Its aperture is sufficiently smaller than the spatial coherence length. And this is used as a virtual light source. So currently, utilization efficiency of synchronous radiation at SPring-8 is less than 0.1%. Therefore, in order to increase the utilization efficiency, we have proposed multi-beam ptychography. So this method was originally proposed for visible light ptychography. So in this approach, multiple coherent beams are used for illumination beam. They don't interfere with each other. Each beam forms a diffraction pattern. In this study, two coherent beams with different wavelengths are illuminated to the sample, and the sample image is reconstructed for each wavelength. So our multi-beam X-ray optics system is shown here. The key point of this system is the arrangement of the multiple slits upstream of the sample. If the distance between the center of the multiple slit is sufficiently wider than the coherence length, and the slit width is set to smaller than the coherence length, so multiple beams do not interfere with each other spatially. The number of the multiple slits is controlled by opening and closing the 4-quadrant slits. So this is the SEM image of the multiple slits fabricated by FYB. The material is a 50 micrometer thick platinum foil, and the slit width is a 10 micrometer, slit spacing 110 micrometer. 3 slits were used in this experiment. The horizontally focusing intensity profiles are shown here. Black profile is 1 beam, and the red profile is 3 beams. The beam spacing is 2.2 micrometer. The distance between the beams, the focal plane, depends on the geometrical reduction ratio, the focusing mirrors. This optical system can improve the intensity utilization efficiency of the synchrotron source by a factor of about 3. The next step is how to reconstruct sample image from the multiple diffraction intensity pattern. So diffraction intensity pattern is expressed as the sum of the diffraction intensities formed by each coherent beam. So then if in the phase retrieval, both the object, the probe are reconstructed from the diffraction intensities, and reciprocal space, the diffraction intensity is constrained by the magnitude of diffraction intensity as shown in this equation. In the real space on the object and probe updating and it's performed on each probe as shown in this equation. So next I show you the result of the demonstration experiment. So as experimental conditions shown here, sample is a 1 micrometer thick platinum foil pattern. The instant X-ray energy is a 6.5 kb, and the number of the beam used were 1 and 3. Here is the SEM image of the sample and schematic diagram of the illumination points. And here the diffraction pattern using 1 and 3 beams. Then the image is reconstructed from a diffraction pattern, reconstructed image for 1 beam and 3 beam. So they are successfully reconstructed. So we have increased the efficiency of the synchrotron radiation source by factor of 3. And the field of view has become increased by factor of 2 for the same measurement time. Okay. Next is a single frame coherent X-ray diffraction imaging of extended object. The motivation here is to achieve dynamic nano imaging. So ptychography requires sample scanning. The measurement takes a long time. This makes it difficult to expand dynamic nano imaging. Therefore, a single frame CXDI of the extended object is needed. To propose a single frame CXDI measurement method. The first one is a keyhole imaging, which was proposed by Keith Nugent group. So in this method, intensity is a binarized of 0 on a non-zero region using the like a top hat beam. The sample can be regarded as an isolated object in a phase retrieval calculation. However, in X-ray regime, it is difficult to form ideal top hat beam. On the other hand, coherent modulation imaging, that is a method improving the convergence of the phase retrieval calculation by placing the phase modulator behind the sample. So this method requires a high positional stability of phase modulator. So both methods are still in development stage. Now, practical approach for a single frame CXDI has been required. So here we first perform a simple simulation for realization of the single frame CXDI. So we simulated the reconstruction of sample image by placing the polygonal aperture just in front of the sample. The sample was an Einstein image like this one, and the aperture were polygonal and circular apertures. The distance between the sample and the aperture was 0.5 millimeter. Here is a flowchart of the phase retrieval calculation. So the flow function is known here. The reciprocal space constraint, the magnitude of diffraction intensity, diffraction intensity as used, and real space non-prior information sample. The sample image is updated on this function. This update function is the same as that used in a ptychographic writable engine. So the important point is that this reconstruction algorithm doesn't use support constraint, no support constraint. So this is the result of the image reconstruction. The image is successfully reconstructed using aperture with non-point symmetry. On the other hand, not reconstructed in symmetrical apertures. The quality of the reconstructed images were evaluated using Fourier correlation, FRC. So this graph shows the FRC values of each reconstructed images. As you can see, FRC value of the reconstructed image using triangular aperture and the pentagonal aperture are close to the 1 entire spatial frequency range. 9-side aperture is no point symmetry, but the FRC value is not close to 1 in the range of the low frequency region. 4-side aperture and circular aperture is not close to 1. Therefore, triangle or pentagon aperture is a candidate for a single frame CXDI. So technically, it is difficult to fabricate triangular aperture with an ideal shape. So corner becomes rounded and edge becomes smooth. So we investigate the accuracy of corner and edge required for image reconstruction. So first, round corner didn't affect the image quality. So we prepared 3 aperture with different edge sharpness. So these are the reconstructed images and the FRC value of the reconstructed images. As the edge becomes smooth, spatial resolution of reconstructed image becomes worse. So spatial resolution is limited by the stiffness of edge of triangular aperture of this method. So then we perform demonstration experiment at SPring-8. So this is a schematic of optical system. This is a scanning ion microscope image of triangular aperture. Its size was about 10 micrometers. So triangular aperture from the platinum foil, and both sides of the platinum foil were polished, and triangular aperture was formed using a focused ion beam. The instant X-ray is cut out by the triangular aperture, then propagated, illuminate the Fresnel zone plate and triangular illumination with a size of about 5 micrometer. It's formed onto the sample. So here are the reconstructed images. Left is a reconstructed image in a single frame CXDI, and right is an X-ray ptychography image. So single frame CXDI took only 10 seconds. On the other hand, X-ray ptychography took about 35 minutes, and sample images were successfully reconstructed from single frame diffraction pattern in a triangle illumination region. So single frame CXDI was reduced by a factor about 200 of the measurement time using X-ray ptychography. So we evaluated the spatial resolution by line scan about achieved 17 nanometer, and we evaluated the spatial temporal resolution. So this graph shows the dependence of spatial resolution on the exposure time. So although the spatial resolution becomes worse as exposure time decreases, the spatial resolution was better than the 100 nanometer, even when the exposure time of the 10 millisecond. So next, I will show you the very, very recent result. That is, we have performed dynamic imaging of the motion of the gold colloidal particle in the solution using a single frame CDI. The sample consists of the gold colloidal particles, 150 nanometer diameter, dispersed in polyvinyl alcohol aqueous solution. That is controlled viscosity. So measurement was taken with 1 second exposure per frame. So this is the diffraction pattern reconstruct image from the frame by frame. That is a Brownian motion. We can see the Brownian motion directly. The motion of the particle is clearly, very, very clearly captured. So the other one is a more funny image. That is agglomeration. So when the viscosity is increased, X-ray beam damages the solvent and cause to the particle to the agglomerate. So anyway, we successfully demonstrated dynamic nano imaging by using the single frame coherent diffraction imaging using triangular apertures. Okay. And finally, future perspective that is towards the use of highly brilliant soft X-ray. That is future perspective and new 3GP synchrotron facility in Japan. That is nanoterrace. That is a motivation is towards the use of highly brilliant soft and tender X-rays. So now 3GP synchrotron ratio facility nanoterrace is under construction in Japan. So terrace is Japanese, not English. So which is equivalent to the illuminate in English. So that is related to the Amaterasu. It's a goddess of the sun in Japanese mythology. So nanoterrace will provide higher brilliance X-ray in the soft and tender energy ranges compared with SPring-8. In particular, I'm focusing on the use of tender X-rays. So tender X-ray, that is no clear definition. Its photon energy ranging roughly from the 2 kb to the 5 kb. Its energy range increases the absorption edge of many key elements from materials and biology. And its bulk sensitivity energy, one can observe inside a bulk sample with a micrometer thickness, but there are not many beamline providing high intense tender X-ray, especially imaging beamline. So this is mainly due to the choice of the monochromator grating or silicon 111 monochromator. So typical hard X-ray beamline cover the energy range from 5 kb and soft energy beamline from 2 kb and below. There are no reports of ptychography in tender energy region. So recently we have developed tender X-ray ptychography system at SPring-8 beamline 27 SUB branch. So which is spectroscopic undulator beamline installed with a differential pumping system. One can introduce low vacuum sample chamber. Here we constructed a measurement system using Fresnel zone plate in off-axis geometry. As a result of the performance test using 2.5 kb X-rays, we have successfully reconstructed the 50 nanometer minimum structure with tantalum test chart. So here we try to visualize the chemical state of sulfur materials. That is also catalyst cathode materials for a lithium sulfur battery. So sample was sulfur polymer particles composed of sulfur and carbon oxygen. So we measured ptychographic diffraction pattern at sulfur K absorption edge. And here the SEM image and the phase and absorption images by ptychography at sulfur K absorption edge. The spatial result then spectral at position 1 and 2 and 3. So we derived the chemical state image here, normalize the phase shift, and SS bond and SC bond mapping. So we found that the surface is rich in the sulfur, and the interior is rich in the carbon and oxygen. The surface is rich in SS bond, and the interior is SC bond. So this is the first visualization of sulfur chemical state by using the X-ray spectroscopic ptychography at tender energy range. Okay, and X-ray coherent imaging beamline, that is the BL10U, now is constructed at nanoterrace in Japan, where high brilliance X-ray beams from 2.1 kb to the 15 kb will be available, increasing the source brilliance by a factor of the 5 to 40 compared to the SPring-8 beamline 27SU and 29XUL. In beamline 10U, differential pumping system will be installed. Liquid nitrogen cooled high precision triple meters and silicon 11 double crystal monochromator will provide highly stable coherent X-ray without beryllium window. So BL10U is expected to improve the spatial resolution and temporal resolution and enable operand measurement. So NanoTeras is scheduled to be fully operational from fiscal year 2024. Okay, I finally summarize my talk. In this study, we developed high resolution and large field of view and high sensitivity X-ray ptychography with using focus mirror optics at SPring-8. Now we can achieve the resolution better than 15 nanometer, field of view larger than the 5 micrometer, and phase sensitivity approximately 0.01 radian. So X-ray spectroscopic ptychography is a promising technique for microstructure and chemical state imaging of a catalyst and battery material at nanoscale. And the multi-beam ptychography can increase efficiency of using synchrotron radiation. So single frame CDI using a triangle aperture is a promising tool for dynamic nano imaging. So 3GP synchrotron radiation facility NanoTeras will provide high brilliance X-ray in a soft and tender energy region. So compared to real SPring-8, so BL10U, that is a coherent X-ray imaging beamline, where in situ and open measurement will be performed using a coherent tender X-ray. At Berlin, I would like to express my gratitude. This work is supervised by Director Tetsuya Ishikawa of Riken Spring Center. And this work, collaborative study with many people listed here. Okay, that's all.